So we are officially live. So Jean-Francois, take it away. It's
okay. Thank you, Sasha. So hello, everybody. Welcome to the RBSP seminar today, this Friday. We have the great opportunity to have a nice talk on the radiation belts and the active experiment from NRL SMART, which will be discussed by two speakers. The first speaker is Chris Crabtree. He's at NRL since 2009. He is the head of the Space Analysis and Application section of the Plasma Physics Division. He's working on turbulence in the magnetosphere, Whistler waves in general, and as you know, on laboratory experiments of all kinds of waves. And prior to NRL, he was a postdoc at MIT working on tokamak plasmas, and before that, University of California at Irvine, working on particle in cell codes. And so Chris will be speaking of SMART in general, and it will be followed by a second talk from Steve Richardson, who's a theoretical physicist at NRL since 2011. He's an expert in ray tracing. He will be speaking about. He has a PhD on this subject. He has co-authored a book on it. And he was before NRL at MIT as well, and Los Alamos as postdoc. All right, so I give you, Chris, the opportunity to start.
Thank you, Jean-Francois. Let me see if I can successfully share this. Okay, is that okay?
excellent.
Okay. So it's a pleasure to speak to you this afternoon. I would like to thank the organizing committee for this opportunity to talk about the SMART experiment and some of the theory that this active experiment will test. Okay. So this experiment has been in the making for almost a decade. So as you can imagine, a great many people have contributed both to the theory and modeling and building the sensors and the shape charge device and the rocket. And so this slide lists some of those main players. And in the interest of time, I'm not going to read all of these names. But first, I should tell you what SMART stands for. It stands for the space measurement of a rocket-released turbulence. So Carl Seifring, our instrument team lead, came up with this name. He's a genius in many respects, and he has a special talent for acronyms. So SMART is a sounding rocket experiment to inject high-speed barium atoms into the upper ionosphere. The experiment uses a 4-stage Black Brant 12 sounding rocket to carry a 200-kilogram shape charge device with a barium liner and an instrumented payload to the top side of the ionosphere. It was scheduled to launch last September from NASA Wallops Flight Facility here in Virginia, but now it looks like it may be sometime this fall and maybe from Wake Island in the Pacific. And at the end of this talk, I'll return to this point. So the rocket will fly to an altitude of about 525 kilometers. Sunlight will illuminate the experiment, but the ground will be in darkness. Timing the experiment depends on satellite orbits. The shape charge device will align perpendicular to the magnetic field, and prior to detonation, the instrumented payload will be ejected ahead of the shape charge device. The experiment needs to be in sunlight in order to photoionize the barium to form a plasma. But the ground needs to be in darkness so that we can detect the photons emitted by both the neutral and the charged barium. And this will allow us to diagnose the amount of barium produced and the speed of the barium injected into the experiment. So this limits our launch conditions down to dawn or dusk, and they're further limited because we would like a remote satellite such as the Eurase satellite to be in conjunction with the experiment and to measure any kind of VLF emissions created by the experiment. The instrumented payload has a large sensor suite, including 3-axis electric field measurements, 3-axis magnetic field measurements, Langmuir probes, and a plasma resonance probe to measure the absolute plasma density. So these measurements will allow us to diagnose the plasma and the plasma turbulence generated by this experiment. So the shape charge device will accelerate about 1.5 kilograms of neutral barium to about 9.4 kilometers per second, creating about 40 megajoules of initial kinetic energy. Barium atoms photoionize on a timescale of about 30 seconds. So this means that the barium cloud will be about 300 kilometers along the direction of injection. The thermal velocity of the barium neutrals will be about 1 kilometer per second, making the diameter of the cloud about 60 kilometers. So the heavy ion beams that are created are unstable to lower hybrid waves with frequencies between 6 and 10 kilohertz, and with wavelengths perpendicular to the magnetic field of about a meter. The lower hybrid fluctuations are electrostatic, so we don't expect them to leave the barium cloud, but they will be intense and they will undergo nonlinear scattering, which will convert the electrostatic wave energy to electromagnetic wave energy, which can then leave the barium cloud, leave the ionosphere, propagate into the radiation belts where they can be hopefully detected. And also they will propagate to the ground. If they can get through the ionosphere, they could be detected on the ground as well. So in the next talk, Steve will focus on where these waves go and how we're modeling the propagation of the waves created in the experiment. So in this talk, I plan to discuss the physics that leads to these electromagnetic waves and hopefully convince you by the end of the talk that active experiments such as these can be a powerful tool to study the natural evolution of plasma turbulence in nature, where the initial conditions can be precisely controlled and known in advance. So in the rest of the talk, I want to try to answer two main questions. The first is, why are we doing the experiment? What exactly are we testing? How is this different from what we can do in the ground, in the laboratory, or in simulations on the computer? I also want to try to give some examples of where the physics that's being tested may play a role in different heliospheric plasmas. In the second part of the talk, I'm going to try to walk through some of the different stages of the experiment and talk about how we're modeling that physics and what that physics is. And then at the end of the talk, I'll give an update on the current status of the experiment. So the basic thing that we're trying to test is the weak turbulence of VLF waves, and specifically waves with frequencies between the ion and electron cyclotron frequency. Theoretical analysis that we performed about a decade ago showed that the most dominant process in turbulent VLF turbulence will be nonlinear induced scattering, and that's given in the bottom box here. It's a kinetic process. It's a resonant process between the beat wave of two waves. So you have two waves and their beat wave interacts with electrons in our case. And this interaction allows the transfer of energy from one wave to the second wave with a residual amount of energy transferred to the particles. This is in contrast to the more commonly studied three-wave processes like three-wave decay or coalescence, which is a fluid process. And in those cases, you have one wave decaying into two daughter waves or two waves combining to create a third wave. So these two processes, both nonlinear induced scattering and three-wave interactions, are part of a general theoretical framework of weak plasma turbulence or wave plasma turbulence, which consists of basically the quasi-linear diffusion equation that describes the evolution of the particles. J here is the adiabatic invariant of the particle in the background magnetic fields, and D1 is the diffusion coefficient that's due to the waves. And so, as you recall, the resonances break the adiabatic invariant and then cause a diffusion. But this equation is not self-consistent, so you need to add the wave kinetic equation to it. This is given here in the linear approximation. And on the left-hand side, you see a kinetic type equation that is very analogous to the Vlasov equation, where instead of following the particle dynamics, you're following the wave dynamics. So you can see here, these are simply the ray tracing equations, which are also Hamiltonian in nature. So there's a direct one-to-one correspondence to the Vlasov equation. Unlike the Vlasov equation, however, we have a right-hand side, which consists of linear terms, both damping and creation. So this can be viewed as a creation and annihilation operators, given the plasmon number density. But you can keep going in this framework to higher orders to include higher order effects. And you can include three-wave decay processes, three-wave coalescence processes, and nonlinear Landau damping into this framework. When you add the nonlinear Landau damping to conserve energy and momentum, you have to add a higher order diffusion term to the quasi-linear equation to conserve energy, where the diffusion coefficient now depends on the fourth power of the wave amplitude. And so at NRL, we are working on a new code called WICKED, which stands for the Wave and Cell for the Kinetic Evolution and Dynamics. This is a tortured acronym, so that gives you a clue that I was the one that came up with this acronym. But this code will solve this set of equations in inhomogeneous plasmas and give you a way of predicting the self-consistent evolution of turbulence and the particles that create and interact with that turbulence. So next, how is SMART different from what we can do in the lab? So at NRL, we are very fortunate to have a very large plasma device to make fundamental studies of plasma processes called this space simulation chamber. It's about 7 meters. Well, the dimensions are given here. It's very large. And so before we started proposing this SMART experiment, we did laboratory experiments to test this nonlinear induced scattering. So to do this, we put a lower hybrid antenna on the side of the plasma. And the antenna geometry determines the wavelength of the fluctuations that the antenna drives. And then we drove it at 10 megahertz, which is between the electron and ion cyclotron frequencies and above the lower hybrid frequency. And we drove it about 10 megahertz. Yeah. And this created electrostatic fluctuations. Because we're in the laboratory, we can make detailed measurements of the fluctuations that are created by the antenna. And what we found is that as we increased the power to the antenna, a lower sideband appeared at 40 kilohertz down from the pump wave, and there was no 40 kilohertz signal seen in the observations, meaning that this was some evidence for nonlinear induced scattering because there were no 3 waves, there were only 2 waves. And we could also use cross-correlation techniques to measure the wavelengths directly. And so here, what I'm plotting in red is for the pump wave, the 10 megahertz wave that we launched with the antenna. And you can see here that its perpendicular wave number normalized to the electron skin depth is bigger than 1, meaning that these fluctuations are electrostatic. But for the signal at 9.96 megahertz, the wave vector it normalized electron skin depth is less than 1. So these are clearly electromagnetic fluctuations. So in the laboratory, we could demonstrate that we can take electrostatic fluctuations and convert them to electromagnetic fluctuations simply by their own nonlinear interaction with the background plasma. And we can verify all of this in a lot of detail. We can verify that I'm showing here the nonlinear scattering rate. It depends on the square of the wave amplitude. So we can calculate, we can measure the scattered wave amplitude versus the pump wave amplitude, and we get a quadratic dependence. There's a threshold that is dictated by the amount of neutral gas in our experiment that provides collisional dissipation onto the waves. We can measure the wavelengths both in parallel and the perpendicular direction, and the frequencies of both the launched wave and the scattered wave, and thus we can measure the beat phase velocity and measure the electron temperature so that we know that the phase velocity of the beat wave is about of the order of the electron thermal velocity. So it's another indication that this is nonlinear scattering. And then the most interesting thing we can do, well, maybe not the most, but an interesting thing we can do is we can test out this method called the wave distribution function, which people developed a while ago to use single point measurements in space to get a wave vector distribution of power. So what I'm showing here is the wave normal angle, which is the angle between the wave vector and the magnetic field, versus the azimuthal angle, which is the angle that the wave vector makes around the magnetic field. And you can see that the pump wave is near the resonance cone. And the scattered wave has both power near the resonance cone, but also at about 45 degrees off of the resonance cone. These contours in black are the theoretical nonlinear scattering rate contours. And so you can see it matches up pretty well. And the most important thing that this shows is this 90-degree turning. So if you look here, this is at about 300 degrees, and this is at about 180. So in fact, if you look at the nonlinear scattering rate, it goes like K1 cross K2 dotted into the magnetic field, which means that this growth rate maximizes when the wave vector in the perpendicular direction makes a 90-degree turning. So this technique was successful in the laboratory, which means we can then take and use this technique using space data, and we can see similar things. So on the left, I'm just putting the same figures from the last plot, and then I'm going to take some data from the Van Allen probes and look at lightning-generated whistlers. And if you take some lightning-generated whistler power and calculate the wave distribution function of the main lightning-generated whistler, you see that it's very near 90 degrees. It's very electrostatic. And then if you look at power just below the lightning-generated whistler power, it's shifted in 90 degrees around the magnetic field, and it's more electromagnetic. So this is some kind of initial evidence that nonlinear induced scattering could be playing a role in the radiation belts, namely from lightning-generated whistlers. I should also point out that the delta B to B for lightning-generated whistlers of this case is about 2 × 10⁻⁵. And in the laboratory, we see these kinds of nonlinear scattering effects at 10⁻⁶. So this is above the threshold. So this is one area where nonlinear induced scattering could be playing a role. We've also looked at solar wind pickup ions, which can create lower hybrid waves and then go and begin nonlinear induced scattering. And also we've applied this nonlinear induced scattering to the kinetic Alfvén wave turbulence in the solar wind at the dissipation scales. Okay, so now I'm going to try to go through some of the stages of the experiment and explain some of the physics in a little more detail, trying to be cognizant of the time. So the first step is we have a shape charge device that will create the initial kinetic energy of the barium atoms. And so Alex Fletcher used the Allegra hydrocode, which was developed at Sandia, to model the shape charge detonation. So this is a movie of that simulation where you can see a high-speed barium jet is created. and there's a as the liner for the explosive is vaporized and then expelled out into the near vacuum. And then there's a slower component of barium that is generated. You can see it about right here. So then what he did is he ran the simulation until you could get to the collisionless regime, and then you can catalog all the velocities of the fluid particles and determine what the barium distribution function that we expect from this experiment. And this will be the initial condition for the plasma dynamics. So you can see this created about a beam of about 8 kilometers per second, a fast beam of 8 kilometers per second, and about a 1 kilometer per second spread in the azimuthal direction. And then there's a more dense, slower component with a maximum velocity of about 5 kilometers per second, but a very large spread. If you combine the barium jet velocity with the horizontal velocity of the Black Brant 12 of about 1.5 kilometers per second, that's how you get the 9.5 kilometers per second speed of the barium neutrals. Okay, so then this simulation has a lot of capabilities. During the development of the experiment, NASA became concerned that we might be creating orbital debris. And so Alex made a catalog of all of the little pieces of the basically the rocket body that would break up during the shape charge detonation, made a catalog of all of the little pieces and their velocities. And you can show then that the velocities are all suborbital. So we're not going to be making any kind of orbital debris from this experiment. The maximum speed is about 4 kilometers per second. It will spread out quite a bit, so we'll have to time the experiment so that there are no satellites going through this cloud during the experiment. So once we have that initial distribution function from Allegra, we can then we'll go through a collisionless evolution, which is basically just a test particle motion. So this movie shows analytical test particle calculations of what the neutral barium particles will do and the charged barium particles. Now, Alex Fletcher also did a very detailed direct simulation Monte Carlo calculation of this whole metastable state transition, and there's a lot of interesting physics. And we did all this detailed physics to try to predict what the optical signatures on the ground will be so that we can get the characteristics of our cameras correct to measure this stuff. But what I want you to take away from this is that in the past, these kinds of experiments have been done before, and it's been sort of taken as a given that this experiment will create a ring distribution in velocity space. And what I'm showing here on the bottom right is the distribution function in the perpendicular plane of the magnetic field of the barium jet. And you can clearly see that it's more of a spiral. And this simply comes about because you have some velocity dispersion, so that the fast particles get to your observing location first, then the slow particles come in after that, and you get a spiral in velocity space.
Hey, Chris, can I ask a question?
Yeah.
So is this all calculated with Allegra?
I'm sorry, this part is done analytically. It's very simple test particle calculation based on the distribution of particles that came out of Allegra. Okay, so one thing we had to do was then make this theory for how a ring instability develops. We had to break the symmetry of in the plane perpendicular to the magnetic field. So these distributions are non-gyrotropic, so it requires us to extend the linear theory, the quasi-linear theory. And what all of this theoretical work led to was this idea that because you no longer have a ring in velocity space, you're going to have a preferential direction for which direction your wave vectors are pointing. And not only that, but the ions that create the waves won't interact with those waves for a very long time, because what happens is that they will generate the waves in a one particular direction, and then the ions will rotate around just due to the cyclotron motion, so that they will not continually lose energy to the waves, or the waves won't be redamped by it. And so you can also predict that you would expect to extract more energy from these non-gyrotropic rings. There's also more free energy available. You could also think of it that way. And so we performed some two-dimensional simulations to basically confirm this idea that these sort of partial rings or rings that are slowly introduced actually give more energy to the waves than you would expect, as if you had just dumped in a perfectly formed ring distribution into the system. Okay, so I see that I'm running out of time, but I want to point out one other thing that I forgot to mention, which is that this whole process of nonlinear induced scattering is a three-dimensional phenomenon. So if you are doing simulations in 2 dimensions, you are going to miss this fastest, most important nonlinearity. And the basic way you can see it is because the nonlinearity comes about because the ponderomotive force due to this convective nonlinearity. And if you work all this algebra out, you can see that it comes out because of the parallel component of the ponderomotive force needs to be able to push the electrons along the magnetic field, and that's best achieved when the electric fields are perpendicular to each other and perpendicular to the magnetic field. However, there is a slower version of this nonlinearity that works in 2 dimensions, and that's what this slide is meaning to show. And the difference between the 3-dimensional version and the 2-dimensional version of this nonlinearity is dependent on the mass ratio. So our colleague Rualdo Soto did a very nice thing where he ran a 2-dimensional simulation of a ring instability, but he kept the mass ratio very low to sort of enhance this 2-dimensional version of this nonlinear induced scattering. And what it's allowing us to do is to develop the correct diagnostic procedures to understand how nonlinear scattering works. And what you can see here is a plot of K parallel versus K perp, and this is a movie. You see the lower hybrid waves being created in the simulation, and the electric field energy and in the magnetic field energy. And then right near saturation, you see these density fluctuations that do not have electric or magnetic field fluctuations that correspond in K-space to them. So then what you can do is take those density fluctuations and pick out a particular K parallel and K perp and follow those density fluctuations as a function of time. And you can see that they're peaking near the time of saturation of the instability, and then they quickly decay. And this is a clear signature of nonlinear induced scattering. So what's happening is the ponderomotive force is pushing the electrons, creating these density striations that then alter the wave behavior, converting electrostatic waves to electromagnetic waves. So we're using these 2-dimensional simulations because they're cheaper, there's less data to analyze, to develop the diagnostic techniques to understand how to work with fully 3-dimensional simulations, for which we're using the 3D VPIC code. And this slide just shows that our wicked simulation can basically reproduce these very expensive particle and cell simulation results. These wicked simulations you can run on a laptop. They're very cheap. And so this is ongoing work. And finally, to the current status of SMART, the rocket is fully constructed. Here's a picture of it. It's been tested. The barium liner was made. The construction of this barium liner, I think, is going to get a Guinness Book of World Record for the largest single piece of manufactured barium. But when the shape charge device was constructed, basically when the explosive material was poured into the container around the barium liner, there was a defect in the manufacturing. And basically it caused a couple of cracks in the explosive, and the barium liner was shifted slightly askew. And so we need to repair this defect. And then the second thing happened was that originally we were planning to launch out of Wallops, Virginia, but it was determined that there's risk of debris landing on Bermuda, and that was, the risk was too much. So we're now looking for alternate sites, such as in the Pacific. So the objective of SMART is to test the role of nonlinear induced scattering of VLF waves in fully developed turbulence. We believe that this is an important mechanism that happens in natural plasmas and throughout the heliosphere. So we think this is an important experiment, and we've had to develop a lot of rigorous plasma physics theory and simulation models to be able to predict this experiment, and we're very excited to be able to compare those results to the actual measurements that we can make. Thank you.
Thank you very much, Chris, for this talk. We are getting a little bit out of schedule. Do we have questions in the virtual room? If you do, please pick up the mic if you can. I don't see question in the, and meanwhile, Steve, if you can try to put your slides, please.
I can ask a quick question if nobody else is jumping in. Excellent talk, Chris. Really outstanding work, both theoretical and apparatus that you put, and the simulations, and of course looking forward to the results of the experiment. I wanted to ask a very basic question. In one of your earlier slides, you when you showed the processes and various approximations that control them, your trapping was not related to weak turbulence regime. Is that the case? There's no connection between trapping and weak turbulence?
Correct. The weak turbulence approximation assumes that the background particles are basically in unperturbed trajectories. And you can make that assumption because the turbulence is so broadband. Basically, there's no, the timescales can't be such that you can get trapping.
But isn't it the case that if you have trapping at multiple resonances and they overlap, eventually you'll get weak turbulence?
Yes, that's one way of looking at it. That is true. That is a good point. That if you that's another way of saying the same thing, I think, is that you need many resonances overlapping so that the unperturbed trajectory approximation is valid.
All right, thank you. I have other questions, but in the sake of time, I'll yield the time, and I'll chat with you all offline. Thank you.
Thanks.
Okay, I ask a small one, if I may. Chris, can you tell us anything about the observation of SMART from space? What is planned, and what do you think is can be measured from space?
Well, in September we had a beautiful conjunction with Arasi. It was so good. I thought maybe it would recur, but when you look at the orbits, I mean, we just missed it. We just missed that opportunity. I'm hoping that maybe in the Pacific things will be different, but yeah, I don't know.
I think you should talk to Lauren Blum, who is here, about possible conjunctions with the GTO spacecraft.
Ah, excellent.
Can I add a quick comment on Sasha's question?
Please go. Yeah.
Sasha, there is another thing about your trapping versus scattering idea, is that Another thing that is not mentioned here was that once you have converted these waves, they are out of the region. They are convected out very quickly because their group velocities of these generators is about 1,000 kilometers per second here. So if you take that into account, there is another time scale that comes in. It's convective time scales or convective damping time scales. If you put that in, I don't know whether the trapping time can exceed that.
All right. All right. Thank you, Guru. I was wondering, did you stop sharing your screen so that Steve can, or Sasha, are you doing that?
No, Chris needs to do that, so he's done.
Okay, so let's continue with Steve Richardson now, and we come back at the very end of the talk, and maybe we have some general question for both speaker, from Steve and Chris, if there's more question. Okay, go ahead, Steve.
All right, thank you, yeah. And thanks, Chris, for that really nice overview of the SMART program. My aspect, as Chris mentioned, is to look at the VLF waves that are going to be generated in SMART and go travel out through the magnetosphere. And I think kind of the physics that underlies what I'm interested in from this experiment would be what really is, what can we learn about VLF wave dynamics in the ionosphere and the magnetosphere? And, you know, obviously we're interested in the SMART experiment. So here's a little diagram. SMART will generate that turbulence. Those waves will get created and then propagate out with this sort of characteristic reflection type of a pattern, and I'll go talk about that in more detail later. But there are other important physical phenomena that occur that you all are very familiar with, including, for example, lightning generated whistlers. And here's some data from a lightning event, actually, that Jean-Francois pointed out to us, that the Van Allen probes got some really nice clean data of this falling tones of these lightning generated whistlers as they reflect back and forth. So we want to see if there's things we can learn about the physics of wave propagation, such as lightning generated whistlers as well. So I'm going to just talk briefly about some background material, the SAMI3 model of the ionosphere and the magnetosphere that we're going to do some ray tracing in. I'm going to talk about ray tracing and how you do that for VLF waves. There's some interesting kind of plasma wave dynamics that occurs for these waves. I'm going to talk about a new algorithm that we've been working on for how to get an estimate of what a spectrogram would look like the one that I just showed you from that lightning event, given some rays. So how would you estimate that spectrogram from the ray tracing? And then it'll show a couple of calculations at the end for these two types of phenomena. So first, this is very brief on SAMI. I am not a SAMI expert. That would be Joe Huba. Fortunately, we have him working in our group, helping us to run SAMI3 for particular times of interest. But SAMI3 is nice because it's fully three-dimensional physics-based model of the ionosphere and the plasmasphere. So it goes all the way from ionosphere all the way out to sort of through the whole plasmasphere where we're interested in these wave dynamics. It includes dynamics for a whole bunch of ion species, electrons. It allows, for example, this picture shows that if you swap out a model for the upper atmosphere neutrals, the winds and so on, from sort of a simpler empirical model to one that's more of a physics-based model, that has some large effects, as you can see in the plasmasphere. It changes what the density structures look like. So it can really capture a lot of this physics of the plasmasphere that may end up being important for these wave propagation. So on to something I'm more familiar with. I'm more of the expert on the ray tracing and the waves. And so just as a background, what we do for plasma waves to do ray tracing is we start with, say, Maxwell's equations plus some model for a dielectric response of the plasma. In this case, I'm using the cold plasma model. It's sort of very familiar from STIX. And what you do is you convert those differential equations for the electric field into what's called the dispersion matrix. And the process you use is, it's kind of analogous to taking a Fourier transform where the derivatives turn into a K, which I've written here normalized as just N. And it gives you a scalar valued matrix. So these functions S, D, and P, they depend on things like the plasma density, the magnetic field strength, the frequency of the wave that you're considering. And then here, the parameter beta tells you what is the wave normal angle of the wave that you're looking at. So what's the angle between the K vector and the background magnetic field? Once you have this dispersion matrix, you can actually use it to generate some estimates for an approximate solution for the wave equations. I call those here sort of semi-classical, and the reason is that this is completely analogous to techniques that have been developed for a long time in quantum theory, where you can get a semi-classical solution by looking at classical trajectories to estimate a quantum wave function. And in a completely analogous way, we can use ray tracing to estimate a solution for what the wave would look like for this particular electromagnetic wave. In order to get those solutions, you have to have a zero eigenvalue of this matrix. So I'm just sort of notation, write that as lambda equals 0. Those eigenvalues are functions of what I call the wave phase space. That's position, wave number, and frequency. Again, determinant is a product of eigenvalues. So determinant equals 0 will say at that point, if you solve determinant equals 0, then that means that there's an eigenvalue that equals 0 there. So this equation is the one that we're interested in. Take some point and ask at that x and k and omega, is the determinant 0? And if it is, then that means that it's a good initial condition for your wave, for your ray. And then you can show that you can write down these Hamilton's equations, and that tells you the trajectory of the ray such that everywhere along the ray, this determinant will remain 0. So it sort of traces out that surface, that solution determinant equals 0. I've written them in a generic form here where it's derivative with respect to tau, where this is just some parameter, but you can rewrite that in terms of group velocity. So you might be a little more familiar with an equation like this for the ray motion is telling you sort of where power is going following this group velocity vector. So here's an example, and I'll try and just point out a few important features here. So in the picture in the center here, I have Earth as the sort of hemisphere on the left, magnetic north is to the top and south at the bottom. This red point labeled A is where I'm sort of initializing a ray. There's several additional lines on here. There's magnetic field lines. This blue dashed curve is perhaps one of the important ones for this particular ray. This is the location where the local lower hybrid frequency equals the frequency of the wave that I'm looking at. And I just put in the corner here a reminder for that expression of the lower hybrid frequency. At a given point in space, the electron plasma frequency, the electron cyclotron frequency, and the ion plasma frequencies all can be sort of combined this way to tell you what is the local lower hybrid frequency. And when that equals the wave frequency, that's an important resonant surface. It changes the wave dynamics. I included a dashed line here. This is because I have just a simple plasma model, and the dashed line is where the plasma goes from being dominated by oxygen to dominated by hydrogen. Okay, so I start a wave at this point A. There's 2 dimensions of physical space. That means my phase space K. The K vector lives in a 2-dimensional space as well. So at that point A, here's a little diagram that lets me think about what does K look like. This diagram is actually showing the phase velocity. So I call it K, but the phase velocity is in the same direction as K. And its length is inverse to the magnitude of K. The little black vector is the direction of the magnetic field. So I'm starting out where the wave vector is sort of anti-parallel to the magnetic field. this blue surface is the location of, for a given wave normal angle, what would the length of k be such that the determinant of that dispersion matrix equals 0? So that tells me what the length of that k vector needs to be. I also have a couple of little dashed lines here. These are the resonant cones for this particular kind of wave. You can't have waves where k is outside. There's no solution in between here. It's a little hard to see on this one because they're so close together, but it's perhaps easier to see over here that there's a region where there are no solutions to the dispersion relation. And now, rather than kind of just walk through all these points, I'm going to try and hopefully this plays. I have a little animation, if it can play. Okay, yes, it's playing. So as the ray moves along, some interesting things happen. The first sort of most obvious thing that happens is that this two-lobe structure turns back and forth. And that's because the direction of the magnetic field determines what the dispersion looks like in phase space. And now another thing that it's a bit hard to see as you watch this, but there's times where these black lines showing that, I'm going to try and run this again. Hopefully it, okay, here it starts again. There's times where these black lines disappear. And that is actually happens when you're inside this little blue dashed lines. And the topology of the dispersion surface changes from being two lobes to being sort of one continuous thing. That's important for the wave dynamics because as the ray moves out here, it's sort of the two lobe structure is sort of forcing K to become more perpendicular to the background magnetic field, but it's not allowed to become entirely completely perpendicular. And that though changes once the ray goes inside this blue dashed line. Now the topology has changed. There actually is a solution for where the parallel component of K can equal 0. And what that means is that actually the wave can reflect. K parallel can change signs. And when it changes signs, the ray changes directions. That causes the ray to sort of bounce back and forth between northern and southern hemisphere. And you can see eventually in this simple model, it reaches kind of this endpoint where there's no longer an allowed sort of reflection to occur, and then it misses it and ends up going to the hemisphere, the southern hemisphere. Okay, so that's an overview of what these ray dynamics looks like. I do want to walk through a little bit, just thinking about the geometry of what these rays look like in phase space. Now it's a little hard because phase space is usually very high dimensional, but you can kind of build up your intuition by thinking about the case where configuration space is just one dimensional. Then K gives you a second dimension. So now phase space would be two-dimensional. The dispersion surface that's described by dispersion function equals 0, that reduces the dimension by 1. So in this case, it goes back to one-dimensional. And then you start a ray and trace out a ray. It actually gives you a structure in phase space called a Lagrange manifold. And that, in this case, would be a one-dimensional surface. That Lagrange manifold is going to have the same dimensions as your configuration space. So for example, if you go to two-dimensional configuration space, your phase space is four-dimensional. D equals 0 gives you one constraint, so that would be a three-dimensional structure in phase space. But your Lagrange manifold then would still be two-dimensional because you need, in order to reconstruct an estimate of the wave, you need geometry that's got the same dimensions as your phase space. So your ray initial conditions are one-dimensional. They then, each initial point becomes a ray as you trace it out, and then that gives you a two-dimensional surface. I've dropped in a picture here from a paper where I looked at kind of a similar case, a lower hybrid wave going through a cutoff. And here I have just kind of a projection from phase space where a family of rays starts along this one-dimensional curve up here. And then when you trace the rays, it traces out this green curved surface that goes through a cutoff. And if you project this in different directions, you get different patterns. So in configuration space, you see the reflection from the cutoff. So this, it looks like this sort of a fold. We call it a caustic, a fold caustic, but you can project to different combinations of coordinates or components of the wave vector, and you can get different kinds of structures. It turns out that at least for me, it's really helpful to think about this geometry because you can do some interesting things with them. And in particular for us, we've been using that to try and develop a synthetic spectrograph. So now I'm going to try and describe how we do that and then show a few results. So I'd like to make a picture like this. So some kind of prediction for what the frequency time spectrograph would look like for these waves. But I want to use ray data to do that. So I'm thinking about the case where I have some sort of observation point, maybe a satellite is up here on the magnetic equator. I start a bunch of different rays. So I have a two-dimensional configuration space, but also time. And then that means my phase space is four-dimensional and I have time frequency data. I'm going to start my initial conditions along a 1D curve here that's a function of magnetic latitude. And then each point, I'm going to use a bunch of different frequencies that start at that point and trace those rays out, and they have this sort of back and forth bouncing. In order to reduce all of this ray data down to something that can give me a prediction for the spectrograph, I have a sort of a geometric problem that this ray data is describing a three-dimensional volume. I can characterize that volume by the initial point of which ray am I talking about, which frequency am I talking about, and then what is the time along that ray. So that's 3 dimensions. The first step in reducing that is to ask, where does that ray cross the magnetic equator? So rather than keeping all the time values, I just watch when it crosses the equator. I record the location where it crossed the equator, the L shell of that crossing, and the time at which it crosses. And that will now give me a set of data that's labeled by which ray am I looking at. So this is sort of now my three-dimensional data. I have which ray am I looking at? What is the frequency of the ray? So that gives me this sort of ray index frequency plane. And then which crossing am I talking about? Is it the first time the ray crossed the equator, the second time, the third time, and or so on? But I've also recorded the L shell and the time of crossing. So on each of these planes, if you think about this as sort of a grid, on any particular grid, I have data for L shell of the crossing location and the time of the crossing. So what I can do is I can create a contour of this data and say, well, here's the contour where L equaled some value of interest. That gives me this contour. And then I have a second function on this grid, if you will, if you think of what is the time that the ray crossed that equator, I can interpolate that time function along this L equals a constant contour. And when I do that, what I get is I get a curve that tells me frequency, which is one axis here, and time, which was the other function that I interpolated. And it gives me a curve in the frequency time plane. And this, I get one curve for each of these crossings. And that is exactly what I need to create my synthetic spectrograph. Here's just another way of thinking of that crossing data. So for one particular crossing, I have recorded the value of what's the L shell of that crossing and what time did the crossing occur. And my family of rays are determined by what is their initial latitude. Maybe it was a low latitude or was it a high latitude? And then what's the frequency of the wave? So was it a high frequency or low frequency? So this sort of distorted mesh here, this is the data that I get from my rays. And you can think of mapping between these two different data sets, the L time data set or the initial latitude frequency data set. And I need to choose particular, what I want is I want the frequency and the time, and that's a sort of a change of coordinates, if you will, of this distorted mesh. So here's an example of applying this algorithm to sort of a simple dipole magnetosphere for lightning generated whistlers. So I traced a whole bunch of rays. Here's my little distorted mesh for each of those crossings. And I'm looking at the observation point, a particular value of L at 2.75. And that value of L, when it crosses these meshes, that's where I do the interpolation. And I get these curves as my synthetic spectrograph. So I should point out this algorithm, like people have created these synthetic spectrographs before. And so I'm not claiming that that's new. The new part here is just the fact that I'm using sort of this interpolation and contouring algorithms on this grid lets me use a much coarser grid, so far fewer rays have to be traced than other methods in the past have required. So in the interest of time, I think I need to just go a little bit more quickly. I'm going to look at one particular example of that lightning strike. I already showed the spectrograph for this before, but that was a pretty isolated lightning strike. And the Worldwide Lightning Network gave us information about where that occurred. So we ran SAMI3 for the appropriate time and the appropriate location on the Earth. And we got a plasma background. And I'm just showing two different slices at two different longitudes to show that there is a three-dimensional variation in our plasma background. And here's an example of one family of rays that was traced in this more realistic plasma background. When I apply my algorithm to that, you can see these meshes are a little bit more distorted. That partly has to do with just the interpolation that I have to do of the SAMI data, but partly that has to do with the fact that these rays are in a more realistic background. But even so, when I apply the algorithm, what I get are these black curves that I've overlaid with the measured spectrograph. And I was honestly quite surprised at the agreement here. So I would say this is pretty good agreement. One thing that's cool that you can do with these synthetic spectrographs is you've got a lot of other information along the ray. So for example, along each ray, I have a wave normal angle. I can interpolate that along the same curves. So here I can plot the wave normal angle. And we can estimate that from data as well. So we can start doing comparisons with data. You can also interpolate some quantities that you can't really get from the experiment or from the measurement. And for example, you could say, well, where did that ray come from? So a ray that gave me one particular part of one of these curves in the spectrograph, what was the magnetic latitude that ray ended up reaching this point? And so here I've interpolated those as well. And there's sort of some interesting trends here that you can see. I'm gonna skip the background of SMART because Chris did a really good job talking about that. And I'm just gonna say that for SMART, the source is gonna look different than the source we're using for lightning because it's very localized. So instead, my families of rays start at one point rather than being located at a lot of latitudes. And instead, I use a range of initial wave normal angles. And when I apply my algorithm for that, I get, again, a synthetic spectrograph, but it has these sort of, the structure of these curves in that spectrograph look different. So this was a simplified plasma background. We can do the same thing where we use SAMI3 to get an estimate for the plasma background. Here I'm contouring again the local lower hybrid frequency. It kind of tells you what the structure would be given this plasma, and it can kind of give you some hints about where you might expect rays to reflect and so on. And so here's an example of a family of rays traced in that SAMI3 background, both looking sort of side on from the Earth, and then this is kind of top down looking at the Earth. And you can see that there actually is some interesting three-dimensional dynamics now, where these rays they're doing the same kind of reflections that we saw before, but they're also, they have some sort of asymmetric spread in longitude. And it turns out that the spread actually ends up being bigger than the plus or minus 20-degree slice that initial SAMI simulation was running. So we've rerun SAMI3 and we're starting to look at ray tracing results over a broader range and longitude. Just one last thing I wanted to mention is there's a lot of ways we can take this. One thing that we are very interested in doing is using some of these tools we've developed to look at, for example, the source of His waves in the plasma sphere. So there's a lot of good work that's been done and a lot of theories about where the energy that contributes to His comes from. And we'd like to use our tools, do some ray tracing in these physics-based SAMI3 plasma spheres to try and answer some questions about the physics of the source of His. I think with that, I will just leave up this summary slide and ask for questions.
Thank you very much, Steve, for this talk and fantastic results. At the end, you presented for SMART. It's very impressive. Do we have questions in the virtual room? Please use the mic if you do have one. Maybe in between, I can ask you, I'm curious about the, just taking the lightning case, for instance, but it will work for SMART too, about the sensibility with the density. Does it shift a lot, the spectrogram that you reconstruct? Do you know that?
So are you talking about the particular density, like, for example, at
the plot where you have
or?
Call and great.
I'm sorry, you're dropping out a little bit.
Would be different if the density was the density model was different. How sensitive is it to that?
I'm sorry, the audio dropped out a little bit for that question.
Oh, sorry, that's this one. Yeah, I think
this plot.
Let me move. Yeah, this one. How would the bottom one would change with density?
Yeah. That's a good question. I mean, I would imagine it's kind of mostly going to be quite similar. There are some features that you see here. You can kind of see how some of these rays end up actually hitting the ground in the southern hemisphere. That is what was giving me these sort of breaks in the spectrograph curves. But that also kind of depends on what the densities look like here, whether or not that local lower hybrid frequency sort of reflection point got hit. So I think there is some sensitivity to that. But this is another direction that I actually am quite interested in myself, is kind of how do you quantify that sensitivity? You know, what if I was going to put, say, error bars on this, like how would I even do that? What would those look like? And so that is something that I'd like to do. Fortunately, these ray tracing is a fairly quick calculation. So I think we can probably start to make some
what do you call fairly quick? What is fairly quick?
Fairly quick. So I'm just running these on like not a very powerful desktop, and each ray is maybe a second or something, which granted it's slow compared to like a nice fast Fortran ray tracer, but this is just a Python code running on my little desktop here. So if I run, you know, a few hundred rays, even on this modest machine, it only is, you know, minutes. So it's a pretty quick calculation, and you know, if we need to, we can probably even speed up the code. So.
I see a question in the chat room from Gianluca Delzano saying, have you tried to compare the field amplitude with data for the lightning generated examples that you showed?
Yeah, Gianluca, that's a great question. So I actually don't have amplitude estimates yet for two reasons. One is that I have not yet implemented any kind of damping along the ray. That's something that you can do sort of in post calculation. Once I have the rays, I can evaluate the plasma conditions along that ray to compute, say, power loss. But another factor that I want to think about a little bit is, and you can kind of see it here, that the rays themselves are spreading out a little bit, and there are geometric factors that affect the amplitude of the waves due to just the spreading. You know, as the rays spread, they kind of spread the power out. And so that's another thing that I need to implement a way to, and I've done it in the past, I just haven't for this code. I need to implement that amplitude calculation.
All right, thank you. Are there other questions? Please use the microphone if you want to ask directly. And we still have Chris, so you can have a question on the first talk as well. It's welcome. I don't know what's the time. Okay, we're past the hour of 5 minutes, so we can you know, close not from so long, but if you still have questions, please go on.
So I was just going to ask, what are some of the sources of dissipation that you mentioned, Steve?
Yeah, that's a good question. There's, well, most of the ones that I would think of are wave particle type of interactions. So power goes from the waves to the particles. There's resonant interactions. Of course, I apologize right now. I'm like drawing a blank on
There's also collisional dissipation, that the wave generated currents dissipate by collisions. That's especially important in the ionosphere where the density is a little high.
Yes, thank you, Chris.
Okay, if we have no other question, maybe just to say, I like very much the plot where you were able to trace the latitude source of each
Yeah,
of the spectrum.
I put this on here because I thought this is giving a lot of insight that you can get from ray tracing that's actually hard to get other ways. I mean, even if I did like a full wave solution of what is the VLF wave, which as far as I know, you can't do that because the plasma sphere is so big. But you can get this information from ray tracing and you can't really from other techniques. So I thought this was kind of really sort of insightful to the structure of what these curves, you know, might be. At least I have a prediction. Where was that power coming from?
Yes, definitely.
Steve,
all right. Yeah, please.
Steve, isn't it true that when you use SAMI for this kind of calculation, the latitudes that can access the satellite location via the VLF wave is different, right?
Yeah, so this is a SAMI background that I used to get this one. Yeah. But it does depend. I'm trying to think. I think maybe this is a good example. You know, depending on which frequency exactly you're talking about, the particular structure of the plasma in the background kind of varies a lot, both as you get to the north side and far south, where the density drops off a lot, but also in longitude. These surfaces look quite different, and that can actually really affect sort of where the waves end up going, and whether or not they reflect or make it to any particular point that might be, you know, your observation point. Not sure if that's quite what you're getting at, Chris, but yeah, the details of the plasma do matter.
Yeah, that's all.
All right, so well, I think we're gonna close the seminar. Thank you very much, Steve and Chris. I'm hoping the best for SMART with an experiment in 2022 and a success of it. So thank you very much again for your talks, and see you all folks in a month for the next RBSP seminar. Thank you.
Thank you.
Bye. Kyle, did you stop recording?
I'm going to stop. It's about a minute behind, so I'm just waiting for it to finish.